Section 3.8, linear approximation. So this lecture will be pretty straightforward. We'll first go over linearization, how to do linear approximation, and we're going to go over two examples. I'll be assigning WebAssign homework in the following few days. For linear approximation, you start with the function f of x. Recall that the equation of the tangent line to y is equal to f of x at the point a comma f of a is the following. Y is equal to f prime of a times x minus a plus f of a. When x is close to a, the tangent line gives an approximation to the graph of y is equal to f of x. In other words, when x is close to a, f of x is approximately f prime of a times x minus a plus f of a. The linearization, this function here, f prime of a times x minus a plus f of a, is called the linearization of f of x at x equal to a. It means it takes the function and changes it into a function whose graph is a line, hence the term linearization. If a, f of a, that is the point on the graph, are known, and f prime of a are known, we can approximate f of x. So what linear approximation is used for is finding the value of a function at a value where we do know the value of the function at a nearby value. Here are the steps. Our first job is to identify the function and a. A should be chosen so that we can evaluate f of a easily. It's a square root function, for example. A should be something like 9, 16, square root of 9 is 3, square root of 16 is 4. We shouldn't be choosing a to be something like 34. I don't know what the square root of 34 is offhand. But actually, we could use linear approximation to approximate a. Step 2 is to differentiate the function and plug in this value a to get f prime of a. So the goal is that we should be able to evaluate f of a and f prime of a pretty much without using a calculator, without doing too much arithmetic, with using the math we know. Recognize the value of x. Step 3 is to recognize the value of x at which to approximate f of x and plug in the values obtained above. F of x is approximately f prime of a times x minus a. So f prime of a, the derivative of the function at the input a value, times the difference between the new value, x, and a, plus the value of f at a. Here's an example. So this is best seen in action. And as the slide says, linear approximation in action. We're going to approximate the square root of 9.03 using linear approximation. Step 1, we identify the function as square root of x. Right? So we're approximating the square root of 9.03. What are we inputting? We're inputting a number. What are we outputting? We're outputting the square root of that number. So the function is going to be square root of 9.03. A, the input. At 9, we do know the output, right? What's the square root of 9? It's 3. Okay, I didn't write it there, but it's square root of 9, which is equal to 3. We also can differentiate the function, that's step 2, 1 over 2 root x, and plug in a is equal to 9 to get the following. F prime of 9 is 1 over 2 square root of 9 times, which is the same as 1 over 6, right? Square root of 9 is 3. 1 over 2 times 3 is the same as 1 over 6. The next step is to recognize that we are approximating f of 9.03, which is the same as square root of 9.03. And so what is x? What's the input value at which we're approximating the output value, f of x? It's 9.03. We're going to plug in, now we have all the values we need to plug into our formula. X, a, f prime of a, and f of a. Here's what we get. F prime of a times the difference between x and a plus f of a. Remember, f prime of a is 1/6. x is equal to 9.03, a is equal to 9, and f of a is equal to 3. So we get 1/6 times 9.03 minus 9 is just 0.03, so it's 1/6 times 0.03 plus 3. 1/6 times 0.03, well, 1/6 is the same as 1 over. Dividing a number by 6 is the same as first dividing that number by 3, and then dividing that number by 2. 0.03 divided by 3, of course, is 0.01. 0.01 divided by 2 is 0.005. 0.005 plus 3 is 3.005. Our conclusion is that the square root of 9.03 is approximately 3.005. So you might have wondered, what did people do with before calculators? How do they find the square root of 9.03 without just punching it into a calculator? This is one thing they could do. They can use calculus to find this value, or at least approximate it. And actually, there's a program. I'm not going to really have time to discuss it in this class, but there is you can use higher order polynomials to approximate a function as well. You get a better approximation. That's actually what your calculator is doing. Here's another example, sine of negative 0.01. You punch that into a calculator, ever wonder how the calculator does that? Well, it actually approximates it. It does it in the sequence of basic operations, multiplication, addition, division, and subtraction. And if the number is small enough, it actually would be sufficient just to use linear approximation. Here's the step. We identify the function as sine x, and a is equal to 0. Right? We know what sine of 0 is, and 0 is close to negative 0.01. F of 0 is, of course, just sine of 0, which is 0. We differentiate the function to get f prime of x as cosine of x, and we evaluate it at 0 to get f prime of 0 is cosine of 0, which is 1. We'll recognize that we're approximating the function evaluated at negative 0.01, which is sine of negative 0.01, so that x is negative 0.01. We're going to plug in x as negative 0.01, a is 0, f of a and f prime of a into our formula. Here's what we get. F prime of a, that was just 1. X minus a is 0 in this case, so this is just negative 0.01. 1 times any number is itself, so we're just left with negative 0.01. And indeed, you might have seen in some other classes, especially a physics class, that sine for a very small angle, whether it's positive or negative, is approximate at an angle. And this is the reason. Because the tangent line to y is equal to sine x at x equal to 0 is just the line y is equal to x. So indeed it is true, sine of x is approximately x for x being small. That's it for linear approximation. I will see you next time.